Okay, so let's compare a couple of poker hands. I'm just going to shuffle these cards up and maybe do a little ripple shuffle. See if we can get a one-handed cut going. Oh, there we go. And now let's deal out two hands of cards. Okay, we don't need these anymore. So now we're going to turn these over and have a look at what we have in these two hands. Now, we're going to notice a few things. One is that these are in no particular order. I certainly don't guarantee that when I shuffle the cards and deal them out that they're going to be in any sort of sorted order. But sometimes the sorting is going to matter, right? Sometimes it matters that, for example, a king is higher than a 10, which is higher than a 5, which is higher than a 4, which is higher than a 2. So that would be information that could be relevant if both of these hands were, for example, just high card hands. However, they're not. So I'm going to sort this hand as well. And now it's going to make it a little bit more apparent that we have a pair over here. So we've got a pair of 9s. So no matter what, a pair of anythings beats high card. Always. Categorically because these are different categories of hands. So this one is always going to beat that one. Now let's look at a couple more examples, and these will be slightly more contrived. So let's say we had our hand with that pair of 9s in it, and then let's say that I took another 5 cards that happen to look a little something like this. So in this case, well, again, we note that there is a pair here, a pair of 5s, and this has a pair of 9s, and the 9s are higher than the 5s, so the pair of 9s wins. What if we had a slightly different circumstance? And I'm just going to pull out a couple of other cards here from my deck, and whether I get to a 9 or a 5. Okay, I got to a 5 first. So let's say instead of 9s versus 5s, that instead we had a pair of 5s versus a pair of 5s. Okay, so then we will compare the 5s, and then we're going to care about the sorted order of what's left. So the 5s are tied, but then next we have a 10 in this hand, whereas in this hand the next card is an ace. So a 10 is better than an ace, therefore the hand on the right is going to win. And let's look at some other examples. So let's say that we've got so here's 3 spades, here's 3 jacks, it's another spade, jacks, clubs, and then there's another spade. Okay, so now we've got 2 flushes. They're all the same suit. So again, if we were to take a look at these and sort them from the greatest to the least, we've got a flush that goes up to a king, whereas over here we've got a flush that goes up to a jack. So the highest card is going to win. There are lots of other kinds of hands that we can get that are interesting. So let's say that we had over here we had 3 5s and 2 4s. All right. And then let's say on the other side we had, let's see, I've seen some kings in here. 2 kings, and how about 3 3s? There we go. All right, in this case, which wins? Which beats the other? So it's going to be, this is a full house of 3s full of kings. This is a full house of 5s full of 4s. And what wins is the more common card. So we've noticed a few things here. We have noticed that that when we have different numbers of cards, such as when we have a pair versus other cards, well, we compare the pair first, and then we compare the other cards. When we've got a full house, we compare the most common card versus the most common card, and then we compare the other ones if we need to. In full house, we'll never need to because you can't have 6 of any one card, so we couldn't have 3 5s here and 3 5s over there at the same time. So first off the bat, there's the categorical thing, right? A full house is always, always, always better than a pair, no matter what the cards are. If they're the same category, then what matters is the most common card that we find. So if we've got 3 of something here, we compare those, and then we compare the other ones. And by the way, this does go all the way down to, so let's say here we had a pair of 5s and another pair of 5s. Surely I must have a 5 around here somewhere. Yeah, there's another 5. Okay, there we go. And then we had a queen and a jack and a 10. Whereas over here we had an ace and a jack and a 10. Okay, so in that case, which one wins? Well, we start with the pair. We compare the pair of 5s to the pair of 5s. All right, that's a tie. All right, okay, very good. So then we look at the next highest card. And we have an ace is better than a queen. Okay, so this one wins. What if, however, we didn't have that ace and that queen, but instead we had this 9 and this 6? What would happen then? Well, we compare the pair with the pair, so the 5s tie. Then we go to the next one called a kicker, and the jack is tied with the jack. Well, so we go to the next one. The 10 is tied with the 10. Okay, we go to the next one. All right, the 9 is higher than the 6. So that means that this hand wins because we go all the way down to the last kicker. So we've learned a bunch of things here. There's the categorical thing of one kind of hand is always better than another kind of hand. If we have 2 hands that are the same category, then it's possible for one to be better than the other as long as the most common card is higher than the other ones. And if we are still tied, then we go from the most common card to the next most common card. So if we have a full house with 3s and 2s, well, we couldn't have a tie with the 3s, but if we had 2 pairs, for example, we would compare the highest pair of each, then the next highest pair of each, and then compare the lowest card. If we only have high cards, we'll compare the highest card, then the next one, then the next one, then the next one, until we find one that is greater than the other. So that is something about understanding the problem that we're faced with in terms of these poker decisions that need to be made. Now, let's start to think about some pseudocode. So what we've learned is that we are going to first need to do some kind of a categorical comparison of 2 hands. So if we, let's draw a little flow chart here. First of all, we're going to find what is the category of the first hand, and that's going to be, well, let's say we don't really know how to do that yet. That's okay. We're going to start by just assuming that we're going to be able to build an abstraction in order to capture that information. So I'm assuming here that somehow we're going to be able to figure out a way in order to determine what is the category of a hand. Now, the way that's going to work is probably by invoking some kind of a function, and that function is going to be its whole own little procedure, which will have boxes and arrows and diamonds and all kinds of fun stuff inside of it. But we don't need to think about how that's going to work while we're trying to figure out what the overall strategy of solving this problem is. So we're going to get a category 1, and then a category 2, and then we're going to ask a question. Is category 1 greater than category 2? If so, then we're done, because hand 1 wins. And if that is not true, so if the category of hand 1 is not better than the category of hand 2, then we're going to need to check the opposite, because it's possible they could be the same category. So is category 2 better than category 1? Well, if so, then we're going to say that hand 2 wins. Right. And then if neither of those is true, then we're going to have to do some kind of comparison of all the cards. And that's something that I'm intentionally leaving extremely vague just for the moment. But once again, it's probably going to involve some kind of a larger procedure that has its own decisions and steps and its own algorithm. But we can start converting even this really, really abstract kind of a flowchart into Python code. So let's take a look at that now. So as always, we're going to write def, and then the name of the function compare hands, and I'm just going to call these hands A and B. I mean, if you want to, you could call them hand A or hand 1 and hand 2 or something, but I think A and B is reasonable enough. People will understand when they're reading our code from context what we're talking about. So as always, it's really a good idea to start with a docstring to help. This helps not just the people who are going to come read our code, but this will help us to clarify our thoughts. If you can't write down what you're thinking, then maybe you haven't really finished thinking it yet. So here we go. We're going to compare two poker hands. Yeah. Very good. And let's describe what they, just to be really, really nice and clear and explicit, both for ourselves and those who come along afterwards. What are the parameters here? So A is a tuple of card strings. And each card string is going to be something like Jack of clubs or 9 of hearts. And then we should probably specify one player's hand. And then B is also going to be a tuple of card strings, the other player's hand. All right. And what does this function return? Well, this is going to return the specification on the assignment page said we should have a 1 if hand A is better than hand B, a -1 if hand B is better than hand A, and a 0 if both hands are tied. If your hands are tied. Okay, so now let's start thinking about how we're going to translate this flowchart. I keep wanting to say spreadsheet. I don't know why. How we're going to translate this flowchart. So the first thing that we said is we're going to get categories for both hands, and then we are going to compare the categories. And then if that doesn't work, then we are going to compare all the cards in the hands. Okay, so get categories for both hands. How does that work? Well, we have already described, or well, we're going to have some kind of a function which is going to get those categories. So let's say that the A category, or category of A maybe, is equal to some function called hand category. So we're going to take A, pass it into hand category, then cat B is hand category of B, and then comparing the categories is going to be as simple as saying if the category of A is greater than the category of B, we will return 1. If the category of B is greater than the category of A, we will return -1, and otherwise we'll have to go on down and compare all the cards in the hand. Now, comparing the hand categories, well, we haven't actually implemented that yet, have we? For the moment, let's just create a little stub of a function here called hand category that does nothing, that just passes. And this will be a place from which we can begin working. Now that we've managed to convert this really high-level view of our algorithm into Python, let's start drilling down into some of the details to make this a little bit more real and maybe make it actually work a little bit. In particular, let's look at this part of the problem where we try to determine what is the category of this hand such that we can compare the categories between two hands. So what kind of a requirement are we going to have on this? Well, first of all, we're going to have a function that we are going to have, it'll be a box, and our little function f, well, maybe f is not a great name. Maybe instead we should call this something like hand category. That might be a nice idea. And then what are we going to do? Well, we're going to pass in a hand which is a tuple of cards. And then when we get that hand, we are going to return something. And what's the something that we're going to return? Well, we want something that can be compared with another hand. So actually, maybe it would be a good idea if we returned an integer. So we could say, well, such and such a hand is it's a category 5 hand, and that is better than a category 3 hand. We don't even have to know what 5 and 3 mean at this point. We don't have to know whether 5 means a straight or a flush. We just need to know that the category of one of these things is better than the other, therefore somebody won. So let's now think about, given that we have an idea of what this hand category function could look like, let's think about what its internals should look like. So how are we going to figure out what a hand's category is? Well, first of all, we know what the various categories of hands are, right? We have a straight flush. And of course, the very best kind of straight flush is a straight flush to the ace, which is sometimes called a royal flush. We've got 4 of a kind. We've got a full house, which is 3 and 2. We've got a flush, which is all cards of the same suit. We've got a straight, which in other games might be called a run, something like 2, 3, 4, 5, 6, or 10, Jack, Queen, King, Ace. Then we've got 3 of a kind, and then we have 2 pairs, and then we have a single pair, and then we have a high card. So if we want to assign an integer value to each of these such that it's easy to compare them, it would be nice if the high card came out as a number 1, pair came out as a 2, 2 pair 3, 4, 5, 6, 7, 8, and 9, all the way up to a straight flush. Okay, so that's the result that we're looking to get here. So let me just move that a little bit out of the way here, and we'll indicate that that is the result that we want. So if we're designing a Python function, then we should return an integer based on what we see. But the question is, how are we going to figure out whether or not these things are true? So let's think about breaking the problem down further using more levels of abstraction. So a straight flush, well, how do you determine if something is a straight flush? Well, that's the first thing we're going to want to check. Is something a straight flush? Well, the way we do that is we check, is it a straight? And is it a flush? If so, then we're going to return 9. Okay, well, how about if that's not the case? Well, what if the most common card, and let's say if the most common card, if we have 4 of them, then we're going to return an 8. If that is not true, well, what if the most common has 3, and then the next most common card, there are 2 of them? So I'm not talking about a value of 3 or a value of 2. I'm saying the most common of them is a 7, for example. Then, oops, erasing things here. Then the next one is, well, what if it is a flush? And if it is a flush, it'll be a 6. What if it is a straight? Then it's going to be a 5. So again, we are kind of coming up with an abstraction that maybe we fully don't understand yet. But in order to answer these questions, what do we need to know? Well, we need to know how to tell if something is a straight. We need to be able to tell we need to know how to tell if something is a flush, and we need to be able to answer things like, well, what are the most common cards in this hand? So, and in the case of some of these, like a full house or in a 2 pair or something, we're going to need to know what are all of the cards in terms of the most common, and then the next most common, and then the next most common. etc. If we can do that, then we should be able to answer questions about full houses, and we should, well, if we already know how to tell what a flush is, and so far, I'm just saying I'm going to assume that I can figure out what a flush is, right? I'm going to assume that I can write a Python function called something like isFlush, and that will tell me whether or not something is a flush. But if I can do that, then I can answer the question about a straight flush or about if so I have idFlush, and if we can write a function called something like isStraight, and if we can write a function that gives us the common or the most common cards, or maybe a better name would even be combo cards, because let's get all the card combinations that exist. If we can do that, we should be able to answer the straight flush question, the most common having 4 question, the full house thing about having 3 and then 2. We should be able to figure out if something is a flush. Well, if we have an isFlush function or an isStraight function, then we can answer the straight question. And the same kind of function that will tell us what are the combinations in this hand will also help us figure out 3 of a kind, 2 pair, and if it's none of those things, so we've got all of these different decisions that are being made, and if none of those things are true, well, I guess it must just be a high card, so we'll return the number 1. So let's see if we can put something like this into some Python code. Once again, let's start with a docstring. So let's describe what we're trying to do here. Convert a hand into a numeric category / score. Okay. So again, we have some parameters, which is a hand, and it's a tuple of card strings. And if we want to, we could even say that, once again, it could be like a jack of spades or ace of diamonds or something like that. And it's going to return an integer representing the strength of the hand. For example, it could be something like 1 for a high card, 2 for a pair, etc. The numbers don't actually matter. All that matters is that the category we return for one hand can be compared to the category for another hand. So if we look at that little flowchart that we came up with earlier, first of all, we need to figure out, is something a straight flush? Well, how are we going to know that? Well, first of all, why don't we actually, no, let's write it this way. So if we had a function called isStraight, so we could ask if that hand is a straight, and if it is a flush, then we're going to return some big number. And I think the number that we said was 9. So we should probably have, and we can delete this pass because we don't need it anymore now that we have real content, so we should probably have an isStraight function, which for the moment, let's say it always returns false, and the same thing for isFlush. Let's say we have these functions, but they don't actually do anything. But this will allow us to imagine that lower level detail is taken care of, but we're going to think at the more abstract level about the problem at hand. Sorry, lots of those puns coming. Then we need to figure out whether or not the most common card is a 4 of a kind. So we said that we're going to have some kind of a function called common cards, or maybe something like hand combos or something like that. Yeah, how about combos? So that function, there's lots of ways that we could write that function, but let's imagine that function is going to return 2 things. Let's say that function is going to return an array of combinations, where that could be something like whatever the value so it could be like a 9 and an 8 and a 2, or 2 or something like that. And lengths is going to be how many of each of those we have. So we've got 2 9s, 2 8s, and 1 2, for example. So we're going to have an array of combos, an array of lengths, and let's get that from I just called it combos, didn't I? From a function called combos. And again, we're not worrying about how we're going to implement that. We just know that's the kind of thing that we ought to be able to implement. So we're going to go on and think about the high level algorithm and not worry about those low-level details just yet. So if we have these combinations available to us and the length, so how many of each combo we have, well, then let's assume, and we can put this detail in a doc string for combos. So combos should find the multi-card combinations in a hand, and it's going to return two things. It's going to return combos, and like we said, that is going to be a list of card values, and it's going to return lengths. How a list of the lengths, maybe the count, list of the count of each card in combos. There we go. And maybe let's have that be a list of card values sorted from most common to least common. There we go. So that could be a helpful thing. So now we're going to have the combos and the lengths. All right, so now we know that if we had 4 of a kind, then our lengths would be equal to something, well, it'd be equal to a list that is 4, 1. So if we want to check if we have 4 of a kind, we can just check if lengths of 0 is equal to 4. Then that must be 4 of a kind. Then next we have if lengths 0 is equal to 3 and lengths 1 is equal to 2. So if we have a combo of 3 and a combo of 2, well, then that's a full house. So we can return 7, etc. If we have a flush, so if is flush hand, then we can return 6. If is straight hand, then return 5. Now this is the point where we might notice, yeah, I've called is flush here and I'm calling is flush again. Yeah, maybe what I actually want to do instead is just call is flush once and store it in a variable, called hand, and do the same thing with straight, is straight hand. And that way we can just check if straight and flush, then return 9, and then down here, if flush, return 6, if straight, straight, return 5, and then what was next? 3 of a kind. So if the first combo is 3 cards, we can return the next number down. If then we've got 2 pairs, so if we've got a pair, and the next one is also a pair, we can return 3. If lengths 0 is equal to 2, return 2, and otherwise we must have just high card, so we're going to return 1. And that should be a complete implementation of the hand category function. So now we are able to compare 2 hands by category. So if one is categorically better than the other, then we will be able to say so. And then, in some circumstances, when hand 1 is categorically better than hand 2, we can take this path. And when hand 2 is categorically better than hand 1, we can take this path. And excellent, that's actually going to cover off a lot of the poker hands that we might be past. It's not going to cover all of them, but it will actually cover a lot of them. So this will get us a lot of the points without having to think yet about how we go through these fiddly details of comparing all the cards. Now that we've done all the other stuff, let's go ahead and think about this business of the comparison of all the cards. So now let's go back and look at some of those details that we left out before. So we have the categorical hand comparison, assuming we know how to tell if something is a flush or if it's a straight, and assuming that we can pull out these combo lengths, or these combos and lengths from a hand. So now let's actually figure out how we're going to implement those things. So how do we figure out whether or not something is a straight? Well, actually, let's start with a flush, because that came first here. So how do we figure out if something is a flush? Well, something is a flush if we have cards of all the same color? No, all the same suit. So all diamonds, all hearts, etc. Which, of course, reminds everybody of that really great moment in Ocean's 11 where somebody thinks he's got a really great hand and he's like, check it, guys, all red. Yeah, anyway. So this video would probably be a lot shorter if I didn't have my little anecdotes, but then it wouldn't really be my video, would it? Okay, so you might be thinking, never mind, I'm going to stop myself, really. Okay, so in order to determine if something is a flush, we have to check and see if all of the cards have the same suit. So how are we going to tell that? Well, we know that a hand is a tuple of cards that could look like 9 of clubs and ace of clubs and jack of clubs, for example, 7 of clubs and 6 of spades. So we're going to be able to look at each individual card. So we might want to iterate over these. For a card in hand, we can do something with those. And one thing that we can do is we can get the value and the suit by splitting that card. Now, we don't actually really care what the value is when we're just checking to see if something is a flush. So actually, let's just get element 1 out of that split. And then what are we going to do with that suit information? Well, we could try to keep track of all the suits that we encounter, for example. So let's see, suits equals empty list, suit equals card.split, suits.append suit. Okay, so now we've got a bunch of suits. Of course, we have another way of writing that, don't we? With a list comprehension. So I'm going to grab the card.split1, oops, and paste it in here for card in hand. Yeah, there we go. So that's a list comprehension, which is just a slightly shorter way of writing down what suits we have. So now, well, what are we going to do? How are we going to figure out whether or not all of these suits are the same suit? Well, there's a bunch of options here. We could, for example, check if we were to take all of the suits and put them into a set. Well, we would expect the size of that set to be 1 because they're all duplicates. So we could return, we could return that the length of set is equal to 1. So that would be one thing. We could also, let's see, use the count method. So we could take that list of suits and we could count how many of whatever the first suit is. And we could ensure that that count is 5, right? And so in that case, we're checking that we have 5 of the same suit. I kind of like that first method better, so why don't we use that? So here we are going to check that the length of the set formed by those suits is 1. So in the example that I gave earlier where we had some diamonds and some hearts, I think the set would have 2 elements in it, which is D and H. So that's how we can tell if something is a flush. If we want to check whether something is a straight, well, in that case, we're going to have to figure out what the values of the cards are. So maybe let's use a list comprehension again here. So values are equal to, somehow we have to get the card value, and let's assume that we can write a function and that we'll figure out how to write that function later. So let's get the value of each card for each card in the hand. All right. And we'll come back to that. But again, we are kind of designing things from the top down by thinking about how would this algorithm work, assuming that someone else is able to take care of the details, where that someone else is just future you, because a future you is good for it. And also, what's future you ever done for you? All right, so we can get all of the values, and then we can do a couple of different things. So first of all, we can check that they are unique. So a straight wouldn't have any pairs or any threes of a kind in it. So if we tried to turn those values into a set and take their length, again, we would expect that to be 5, right? So if the length of that set is less than 5, then that means that there must be at least one duplicate in there. And so we're going to say, no, that is not a straight. Okay. Alternatively, yeah, let's leave the special case out for the moment. Come back later. And that's where we're going to think about the low straight, but that's something we can talk about later. So now that we've determined that we have 5 different cards and 5 different values, we need to make sure that their values are all in a row. So one way we could do that is if we have those cards in a sorted order. There we go. Then we know that they ought to be, for example, values 4, 5, 6, 7, 8, which means that the last one minus the first one ought to be 4, right? 4, 5, 6, 7, 8. 8 minus 4 is equal to 4. And you can work out a few examples on paper to convince yourself that that is true. So let's check. Are all values contiguous, which just means one after the other. So let's return whether or not values 4 minus values 0 is equal to 4. So that would be one way to check, assuming that we've figured out how to get these card values. Now, we haven't actually said how we're going to do that yet, so let's do so now. If we can get a single value from a single card, how are we going to figure out what the value of a card is? So again, let's have a nice docstring, convert a card into its numeric value, and this is going to return an integer from 2 in the case of a deuce or a number 2 up to 10 for, well, the number 10, all the way up to something else for an ace. So one way that we could choose to represent the value of these cards is we could, so let's see. First of all, we're going to do the same trick that we did earlier. If we're going to split the value and the suit out, and we don't really care what the suit is, so we could just say value is equal to card.split 0, but yeah, there's no harm in doing it this way, and it does make it kind of clear and explicit, so why not? Why don't we say if the value is equal to the letter A, then let's return the number, well, 10, so a jack will be 11, a queen will be 12, a king will be 13, so an ace will be 14. So all the way up to the number 14. So if the value is A, then we'll return 14. Otherwise, if the value is K, we'll return 13. Otherwise, if the value is Q, we'll return 12. Otherwise, if the value is J, we'll return 11. Otherwise, what? Oops, don't need a colon there. Else, we will return, well, at that point, I guess the value must be a string representation of a number. So it could be the letter 6, or it could be the letters 1 and 0. Whatever it is, we ought to be able to turn it into an integer. So this is how we can get the value of a single card. So now we have implemented the isStraight function. We pass it a hand and it will tell us, is it a straight? Here we have a card value, very good. And here's the isFlush function that tells us, is this hand a flush? So based on all of that, the only thing that's left to do is implement this combos function. And that's going to turn out to be really critical. That function, well, I mean, all of these are pretty important, but that one is kind of the crux of what's left, and it's sort of the part that we have to think a little bit more carefully about. So the last thing for us to figure out is how to implement this combos function. How can we look at a hand and then figure out which combinations of multiple cards we have? In order to do this, we're going to have to do a couple of things. One is we're going to have to, for each value in the hand, we're going to have to count how many of those cards we see in the hand. And then once we have the counts and the values, then we're going to have to move them around into some sort of an order that will allow us to return the things that we promised to return, which is a list of the combination values and a list of the combination lengths. So let's think about how we do this. So there's, as always is the case in programming, there's more than one option here. One thing that we could do is use a dictionary. So this would kind of make a lot of sense. If we have a dictionary that maps from card values to the number of cards that have that value, that would make a certain amount of sense. So let us go ahead and create an empty dictionary here. And then we can iterate over all of the cards for each card in the hand. If we have seen, so let's get the card's value first. Card value, there we go. Then if we have seen a card with this value before, then we will add 1 to the count that's being stored in the dictionary. So if that value has been seen in combos, then we can simply increment that values. Combos value plus equals 1. Otherwise, if we haven't seen that before, then we will set combos value to be 1. Okay, very good. This is a point, by the way, where counting in this way would be absolutely fine. There are other ways that we could count, again, with a dictionary. But one thing that I might like to do here is I'm going to import a module called collections. And I mentioned this when we talked about dictionaries before. You see how I've got like 7, 8 lines of code, something like that. Instead of manually checking, do we already have this value? If so, I better treat it specially or differently from if we don't already have the value. Instead of creating a regular dictionary, I'm going to create a default dict. And so this default dictionary will pass in. Well, actually, we're passing it is not just a type. We're passing in a function to it. And this is saying, dear default dictionary, anytime you try to look something up and that doesn't exist, instead of giving an error or something like this, just use this function to construct a new one of them. So int is actually a function, and if you call it, you can see it returns, or it evaluates, well, yeah, the int function returns to 0, so the function call evaluates to 0. This allows us to simplify the code quite a bit, because now we don't have to check if that value already exists. Instead, we can simply increment whatever it is by 1, because if it doesn't exist, then it will be initialized right then to contain 0. However, if you're not fond of, this is a little bit shorter code, however, the longer way also works just as well. So now we have a count of how many instances of each card value we have. Why don't we get rid of that pass, because now that we have actual code, we don't need it anymore. So one thing that we would like to do now, we could, if we wanted to, say, all right, well, our lengths array, our lengths list that we're supposed to get is if we have a length, a value and a length in each item within combos. There we go. So we could create lengths and we create values like this, and then we could return lengths and values. And this would almost fulfill the contract of this function, in that the function says it's going to return a list of card values, and it's going to return a list of the count of each card in those combos. But the part that's missing is it needs to be sorted from the most common to the least common, because we are not interested in having some arbitrary ordering, right? Like if we have a pair, for example, I don't want, if I have a pair of 9s, then I don't want lengths to end up being 1, 1, 2, 1, with values being like 4, 5, 9, 14, or something like that, right? Because in other places we're checking, well, is lengths 0 equal to 2, because that would be a pair. No, so instead we need to make sure that we sort these things, but we need to sort by the length and not by the value, which is kind of interesting. So one way that we can do that is we can use so we could create a list that contains a bunch of tuples, where each tuple is a count and a value. So count value for value count in combos.items. Okay, so that is a list of tuples where each tuple is a count and a value. Now, why did I put the count first and not put the value first, right? Why couldn't I just, for example, let's sort this. So a sorted version of that. Why couldn't I just write sorted combos.items? Well, that's a good question. I'm glad you asked. And so if we had the example from earlier, so let's see, if I had a list that was something like, what did I say? There is 1 4 and there is 1 5 and there are 2 9s and there's 1 ace. Okay, let's do that. If I try to sort this, then you're going to see that by default, Python likes to sort by, well, actually, I gave it a sorted list in that case. Python likes to sort by the first element in the tuple. So that would be sorting by the card's values, going from lowest to highest. But we don't want to sort by the card's values. We want to sort by the number of cards that we have. So instead, we want something like 1, 4, because there's 1 4, and there's 1 5, and there's 2 9s, and there's 1 ace. There we go. So we sort these, and okay, now we're sorting by how many of each there are. And you can see that we are using the value of the cards to sort of break the tie, if there is a tie, because there's a 4 and there's a 5 and an ace. And so we've put them in the right value order, but the number of cards is more important, so that's good. Now, the only other thing that's missing here is we want the reverse order. So the sorted function takes... it has a parameter called reverse, and we're going to pass true to that parameter. Okay, so let's do something like that then. So we are going to, let's see, counts and values is equal to, well, just to be nice and clear and explicit in one step at a time, counts and values is equal to count or a list of count and value for each value and count in combos.items, and then we can change that, or we can counts and values, we can just call this sort method on that and pass reverse equals true. So the difference between the sorted function and the sort method is that the sorted function will return a new list, whereas the sort method will sort those things in place. So now that we have sorted counts and values in the correct reverse order, so we will be sorted from the most common cards to the least common cards, and within combos that have the same number, we will sort from the highest to the lowest. So that means if you have 2 pair of aces and 10s, then the aces will come first and then the 10s, and that's good because we want to compare the values of these cards from the highest down to the lowest, my highest versus your highest, my second highest versus your second highest, etc. So now the only thing that we need to do here is change these things around. So instead of building lengths and values out of combos.items, we're going to build it out of counts and values. But in doing so, we better reverse these 2 things around, because each item inside of counts and values is a count and a value, not a value and a count. At some point, I changed from saying length to value because, well, we don't really need, it's not really a length anymore because we're not actually storing like a list of cards here. We are just storing the count of how many there are. Okay, and so at this point, we now have a complete and working solution to the problem as was set. there's only, and you see it's 132 lines of code. The solution I post is going to have more comments than this to kind of explain some of the things that I'm doing, because that's a good practice. But the only thing that is missing from here is, what do we do about the thing I said we would come back to? What is the special case? So there is a bonus question, which I kind of mentioned in one of the lectures, that there might be a bonus question along these lines. I said you didn't have to take into account the fact that an ace can actually be high or low. So an ace can participate in a high straight, 10, jack, queen, king, ace, or an ace can participate in a low straight, ace, 2, 3, 4, 5. And so when we're checking to see if something is a straight, this check for contiguous values is going to cover all of the straights except the low straight. Now, I told you didn't have to worry about the low straight, so that's absolutely fine if you didn't. If you didn't, then, well, you just wouldn't get the bonus mark, but that's okay. It's a bonus. You can still get 100% without getting the bonuses. However, if we did want to get that bonus mark, the only extra thing we'd need to do is check whether or not the values are equal to ace, 2, 3, 4, 5, right? So 14 was the value of ace, 14, 2, 3, 4, 5. Now, the trick is, this is not really sorted in any particular order, so we could, if we wanted to, check if, let's see, actually we already have values is sorted above, so if values is equal to 2, 3, 4, 5, or 14. That's one thing we could do. Another thing that we could do is, and I think this is what I've got in the solution that I prepared earlier, which I'm also going to upload. I actually decided, for whatever reason, I was going to use a set. So I was going to check to see if there were 5 cards and if they were these 5 cards. One reason to do that is in a set, if you're checking set equality, ordering just completely doesn't matter at all. So I'm just checking to see if these 5 cards are in the set. And if so, we'll return true, and we'll say that although this doesn't really look like a straight, it is a straight because the 14 in this case is behaving as a low card. And so if we did something like that, then we'd even get the bonus question. So that's how we can solve this assignment. And I've talked about a few different options. This is, maybe slightly longer than I anticipated it being. However, I hope it's really helpful for you that we've had an opportunity to review a bunch of things. We've looked at how we do top-down design of the solution to a problem. So how we can think about big picture algorithms, and well, as long as we have a function that can do such and such, then I know how to do this top level thing. So here, as long as I, sorry, no, there's one element missing here. I didn't actually go back and finish this last part, comparing all the cards in the hands. However, I think you're going to see that it is fairly straightforward. So now that we know that we are able to get those combos, so combos and counts from A. So we have a function that will tell us here are the most important or the most frequently repeated cards from the most common to the least common. And within those, here they are from the highest to the lowest. You're going to see that combos B and counts B is equal to hand combos B. Okay. And now all we need to do is compare each of the combo cards from one hand and the other. We know, because we've gotten to this point in the code, we know that categorically they're the same category, right? We're not talking about 3 of a kind and 2 pair or something. So we know that if there's 2 pairs in one, then there's 2 pairs in the other. So combos A and combos B will be the same length. Counts A and counts B will be the same length. Sometimes when we know something really, really, really ought to be true, we will actually write a statement here called an assertion, which basically documents that A, the programmer is assuming that this is true, and B, if this is ever not true, the Python interpreter can actually check and see if it's true. And if it's ever not true, it will cause the program to fail in a really obvious way that says, hey, your code made an invalid assumption, so something's broken here. And so that's a useful, better than having like silent failure with data corruption or something. So now all we need to do is iterate over all of the values inside of both of these. So range, not rang. And we can check that if your highest or if your most common combo, so your 3 of a kind, for example, or if A's most common combo is greater than the value of the card in B's most common combo, so I've got 3 kings and you've got 3 jacks, well, then I'm going to win. Otherwise, if it's the other way around, then you're going to win. Otherwise, we just keep going through this loop. And so I'm going to compare my best combo with your best combo. Then I'm going to compare the next one, the next one, the next one. So, and note that this code is the same for all of the various types we care about. If you have a flush to the ace and I have a flush to the ace, then we might compare my ace with your king, my ace with my ace, my king with your king, my 10 with your 10, then I have an 8 and you have a 7. Okay, I win. If, however, it is actually possible to have, for example, 2 flushes that have exactly the same values in them, or 2 straights that have exactly the same values, or 2 pair, right? I could have 10s and 7s, you could have 10s and 7s, and we could both have a 5 kicker. Okay, well, in that case, it is in fact a tie. So if we go through all of our combos and they are all equal, then I guess it's a tie. And then the 2 hands actually tie. And notice here, I don't care which category of hand I have. This logic works whether I have a flush or a straight or a full house or 4 of a kind, or it works for any straight flush. It works for any of those various types. And so there's a nice example of how we can separate different aspects of a problem when we think about how to solve the 2 parts of the problem independently. There's an opportunity to sort of divide and conquer the problem, and there's an opportunity to end up with code that's fairly straightforward and fairly simple to read. There's one little fiddly detail here, which is this business about a function that can figure out what combos you have, but we should have an instinct that that's the kind of problem we ought to be able to solve. Another little note I'll make here is that we're not actually using these counts anymore. So one thing that's kind of common is if you are extracting 2 variables from a tuple that's returned from a function or something like that, but you're only using one of them, a single underscore is actually a valid name for a variable. It's not one that we recommend using for a real variable, but for this kind of purpose, it's often used to kind of say, please just ignore that. I mean, it's a variable and it does technically exist, and we do technically need it to exist because otherwise we'd have a syntax problem. But this is kind of a nicer and cleaner way in some ways of saying basically this. So instead of saying we're going to get something back from hand combos and we're going to take element 0, instead here we're saying there are exactly 2 things that are coming back and we only care about 1. Right, so as I was saying, we now have a complete solution in 145 lines of code. It'll be more once I upload, when I upload the previously done version that has more comments in it. But this shows us how we can break a problem into parts, starting from the highest level problem, and then develop levels of abstraction to say, okay, as long as I know how to categorize a hand, I don't need to worry right now about how that works, but as long as I know how to categorize a hand, well, then I can compare those categories. And then if I know that we're in the same category, as long as I can figure out what the most common and then the most valuable combos are in somebody's hand, then those are things that I can compare. And then we thought, okay, how do we implement or how do we categorize a hand? Well, if we need to know if a hand is a flush or a straight, if it's both, it's a straight flush, then we can get the combos for a hand and then we can check if the most common card is a 4. Well, that's better than a full house, which is 3 of a kind and 2 a three of a kind and a pair, and then there's a flush, then there's a straight, and then there's a three of a kind or a set, and et cetera, et cetera. And that relies on the ability to check, for example, is this thing a straight? Well, in order to check that, we need to know what the values of the cards are. In order to do that, well, we need to either convert a number into, or convert a string into a number, or to convert the string into a number manually by assigning a value to it, and et cetera, and all the way down. And so you can see all of this kind of, these lower level functions get used by higher level functions, would get used by even higher level functions. So here is a nice example of how we can build abstractions that allow us to hide some details away so that when we're thinking about the big picture, we don't have to sweat the small stuff. As long as we are then capable of going back and sweating the small stuff at another time when we don't have to worry about the big picture. Sometimes we think about the big picture, sometimes we think about nitty-gritty details, and they're both important, but it works best when we only have to do one of those two things at a time. So I hope this is a helpful example, not just of how to solve this specific assignment, but another example of thinking through the design process, as well as a reminder of how a few data types work, like sets and dictionaries and lists, and then what a list comprehension is and stuff like that. So I hope that is very helpful for you. You gotta know when to hold 'em, know when to fold 'em, know when to walk away, know when to run.